All right, welcome to physics. We're going to try doing a flipped classroom this year, probably chapters 1 through 13, and then you ask, well, how many chapters are we going to get into this year? And usually, depending on how things play out and with snow days and all that jazz, probably 22, 23 chapters. Physics is kind of broken down into two categories. You have Newtonian physics, and then you kind of have sound, light, electricity, magnetism as your second category. So we spend a lot of time on Newtonian physics, and I think it's going to be really beneficial to do the flipped classroom for this. And the reason being is a lot of times we go through the notes in class in the past. Your assignment is, 5, 6, 10 problems. You come back the next day, I didn't get problems 8, 9, 10, 11, 12, 13, 14. Well, that's not going to do you any good. So by doing this flipped classroom, you're able to watch the notes at home, look at the example problem, and then we're going to do the homework in class. And I think it's going to be really beneficial for you to do the problems in class when I can help you out. So with that being said, let's go ahead and start Chapter 1, Section 1, Physics and Mathematics. This section is really just an introduction to physics. What are we talking about with physics? Well, if you go back to 2 years ago when most of you had biology, and I asked you, what is biology? Biology is the study of life. So the study of life. Chemistry, which most of you had last year, or some of you are taking this year, chemistry is the study of matter. Well, physics is how that matter interacts. So the big idea here is how they interact and how they're related. So we're going to be talking about motion, energy, force, electricity, and how all these outside forces affect things. So we're going to spend a great deal on gravity. How does gravity affect things? How does it interact? All right. If two objects collide, how are they going to interact? What forces do two objects have if they are far away from one another? All right. How does static electricity work? That is a force. So we're going to spend a lot of time dealing with forces and motion and all sorts of stuff. There's thousands and thousands of occupations you can get as a physicist. The basic ones are astronomy. You can be an astronomist, an astronomer, not astronomist, astronomer. Engineer, computer science. Or for example, Carly Crowley's going to school to be an orthopedic specialist. Well, orthopedics is a perfect blend of physics and kind of health science, where you have to fit that orthopedic or that brace or that leg, all right, someone's leg, to fit them perfectly. Everyone's legs is different lengths, they have different ranges of motion, and you kind of got to figure that out. So that's kind of physics in the real world. But physics and mathematics. And when we talk about mathematics, what are we going to be using this year? All right. What are we going to be using this year in this course? This course is very math intensive. So we're going to be using a lot of algebra, a lot of geometry, a little bit of trig, and just a pinch of calculus, not a whole lot of calculus. So don't flip out if you don't know how to do calculus. You're going to learn as you go. It's not going to be a big deal. There's like one little section, and I'm going to teach you how to do it. So don't be freaking out if, I got to drop this class because I don't know what physics is. All right, but when you do math, and anytime you do math, you got to ask yourself a couple things. First things first, does it make sense? All right. If I'm doing a problem and I figure out a car to be going 250 meters per second, does that really make sense? Can a car really go 2.5 football fields in 1 second? Probably not. So you kind of have to be aware of your answers. And then units are extremely important. And remember, we use the international system of units, which mostly is based in the metric system. We use these in chemistry last year. You're very familiar with them in science, but they get used a bunch in physics. So we look at what are our base units. Anytime you're doing a problem in physics, you are going to want to have these base units. So meters for length, kilograms for mass, and seconds for time. All right. Remember, we use Kelvin, because Kelvin's the only temperature that does not have a negative value. You can have negative Fahrenheit, negative Celsius, but you can't have negative Kelvin. We talked about moles last year as an amount of substance, and electric current is just an amp, and we'll talk about that way at the end of the year. But how do we get other units? All units are derived from these base units. Well, what do we mean by that? Well, you know that in the United States, for speed, we go miles per hour. In the metric system, we go meters per second. But how exactly did we get that? Well, remember, velocity is equal to distance divided by time. The unit for distance is meters. The unit for time is seconds. And that is how we get meters per second. Now, it'll get a lot more complicated when we're throwing in 3 or 4 or 5 or 6 different base units all at once, but this is how we derive all of our units. So length is meters, mass is kilograms, time is seconds. That should be basically review. The second thing that should be basically review is metric prefixes. And these are on page 6 of your textbook, and you're going to have to know these from nano through tera. And the one thing to talk about when we talk about metric prefixes is they always go in thousands. So every exponent changes by 3. So you're going to start with nano, which is 10 to the negative 9th. And then your next one will be micro, 10 to the negative 6th. The next one will be milli, 10 to the negative 3. Your base units, 10 to the 0. And as you work your way up, you're still increasing by 3. Kilos, 10 to the 3rd. Megas, 10 to the 6th. Gigas, 10 to the 9th. And tera is 10 to the 12th. And those are you're going to have to know. Now, why do we have to use those prefixes? Because in physics, you're talking about how things interact. Well, you can be talking about 2 atoms interacting, which is a very small scale, or you could be talking about 2 universes interacting, which is on a very, very large scale. So that is why we have to deal with these prefixes. So page 6, nano through tera. Don't be surprised if there's a short quiz on those. Secondly, you guys are going to have to work with dimensional analysis when we talk about math. Now, for anyone who had physics last year, these are the railroad tracks. And this is how we convert units. All right. So how do we convert, for example, if I had a question, if something is going 50 miles an hour, how fast is that going in meters per second? And for you in chemistry, it's going to look very... All right, you kind of get the idea how to do that. For the rest of you, we can kind of go through here on the next slide and let's do an example. All right, and the example that I like to use is Usain Bolt. All right, Usain Bolt is the world record holder in the 100-meter dash. He runs at 9.59 seconds. That averages to 10.4 meters per second. Now, for everyone but Aurora, we have no concept of what 10.4 meters per second is. All right, our base unit is miles per hour. So what is 10.4 meters per second in miles per hour? Well, we are going to work with converting meters to miles and seconds to hours. So we can convert that to miles per hour. Well, how are we going to do that? Well, we're going to start with our unit, 10.4 meters per second. And in dimensional analysis, what you are working on is you are canceling units. And you cancel units just like you can cancel numbers in a fraction. So if I had a fraction, for example, that was 6 over 5 times 5 over 8. All right. What could I do? I could automatically cancel out those 5s, and I know my answer is 6/8. All right. We can do the same exact thing with units. Well, how do we do that? Well, let's go over here. We know that we have to go from meters to miles. All right. We have to go from meters to miles. Well, if we have to do that, I want to get rid of meters. So I'm going to put meters on the bottom so that cancels out, and I'm going to miles. What I'm going to do next to that is I'm going to put my conversion units. And in 1 mile, there are 1,600 meters. And you're like, well, how do you know that? Well, think about it. If you're in track, how many times, or in Phi Ed, how many times you got to run around the track to run a mile? 4. And 1 time around the track is 400 meters. So 1 mile is 1,600 meters. Our units cancel, our meters cancel, and if I were to leave this, my new unit would be in miles per second. But remember, I do not want that. I want miles per hour. So I'm going to do a second railroad track where I'm going to try and get rid of seconds now. Well, seconds is initially on the bottom, so now I'm going to put that on the top, and we're converting seconds to hours. So I'm going to put hours on the bottom. And in 1 hour, how many seconds are there? Well, 60 seconds in a minute, 60 minutes in an hour. 60 times 60 is 3,600. Right. Again, my units cancel. My seconds cancel. And now, if we look at my units are miles per hour, which is what I want. So now I'm going to just multiply and divide. I'm going to take 10.4 times 3,600. And when I get that, I get 37,440 divided by 1 times 1,600, which is 1,600. I'm going to divide these. And when I divide, I end up getting 23.4. So my answer is 10.4 meters per second is 23.4 miles per hour. Now, you got to think that's pretty neat in the regards of that's how fast his average speed was during the whole race. You have to remember at the beginning he's going slower and at the end he's going faster. So it's very feasible that at the end of the race Usain Bolt is going faster than the legal speed limit in Main Street, downtown Hayfield. So that is fast. So that is what we have there. So that is dimensional analysis. That is math. The last bit of math, and the biggest thing that we have to worry about for the entire year in physics is we have to worry about significant figures. Now, you've all had significant figures in 9th grade, and we touched very briefly on it in chemistry last year. So if we review real quick, if I draw 3 numbers down here. All right, let's review. If you get these, you can probably just kind of skip right through this slide. 876,000, how many sig figs does that have? 3. 0.00401, how many does that have? 3. 701.02, how many does that have? 5. Sig figs are a big deal. And why they're a big deal is you can only be as accurate as your least accurate measurement. So keep that in mind. So if I only measure out to 2 places, for the most part, my whole answer has got to be in 2 places because that's all the farther I measured. So what are our general rules in sig figs? All non-zeros are significant. So number 1 through 9, it's automatically going to count. So we're really only focused on zeros because 1 through 9 is significant. So we have to focus on zeros. Well, there's a couple 2 rules for zeros. Rule 2, leading zeros to the right of the decimal are not significant. So for example, 0.000045. Those 4 zeros do not count, and 0.000045 has 2 sig figs. We go over 0.000134. Those 3 zeros do not count. So my number of sig figs is 3. Now likewise, I could have an answer like this, 0.000600. Which ones count and which ones don't? Well, to the right of the decimal, leading zeros. These 3 are the only leading zeros. The other 3 numbers are good because I measured those 3 numbers. So 0.000600 would have 3 significant figures. Next up, rule number 3. Trailing zeros to the left of the decimal are not significant. So 2 examples. I do not write my decimals like that. I've never put a 0 in before. But if you put 0 point whatever for your decimal, that 0 never counts. So 0.345 automatically has 3. Trailing zeros to the left of the decimal. Well, on 14,000, if you pretend the decimal to be there, these 3 are trailing that decimal. 14,000 would have 2. Now, one thing you got to be really careful about, 14,000 decimal. If I have that decimal point there, that means I measured every single number. So 14,000 is exactly 14,000. If I take away that decimal, we go back to 2. But with the decimal at the end, 14,000 decimal has 5 sig figs. And we'll have some time to practice on class with sig figs. Then, what's going to affect us the most with sig figs is, do not worry about adding or subtracting. We are going to rarely add or subtract with sig figs, but what we will do is we are going to multiply and divide all the time. And when the rule for significant figures is when you multiply and divide, you have to keep the fewest amount of sig figs. What does that mean? We have 2 really basic examples on the bottom. We have 125, which has 3 sig figs, times 11, which has 2 sig figs. You have to keep the fewest amount, so the smallest number between 3 and 2 is 2. So our answer has to be in 2. If you take 125 times 11, you're going to get 1375. We round that to 1400 since that has 2 sig figs. Next example, 144 is 3, 6 is 1, which means our answer has to be in 1 sig fig. 144 divided by 6 is actually 24. But to get that to 1 sig fig, I have to go to 20. So if we look here, we have 3 examples. And when we do these 3 examples, we're going to do sig figs with the numbers. But the other thing that's important is you want to multiply or divide your units so your answer has the correct number of sig figs, but also the correct number of units. So we take a look at this, 6.201 times 7.4 times 12.0. Well, let's go through right away and figure out how many sig figs. 6.201 has 4, 7.4 has 2, and 12.0 has 3, which means that our answer has to be in 2. So when you take 6.201 times 7.4 times 12.0, you end up getting 550.6488. Well, how do we make that into 2 sig figs? We're going to make that into 550. Now what's key is our units. We have centimeters times centimeters times centimeters. So our units would be centimeters cubed. Next up, number 2, 123.423. Well, there's no zeros in that, so they all count. That's 6 divided by 84.3. Again, no zeros, so that's 3. So we have 6 and we have 3, so our answer has to be in 3. And you take 123.423 divided by 84.3, and you end up getting 1.46409. You have to take that and make that into 3 sig figs. 1.46. Look at your units. You have meters divided by seconds. So our unit is going to be meters per second. Last one up. 139. Well, that's easy. Again, I got no zeros in there. So that's 3 times 2.3, which is 2. So we have 3 and 2. Our answer has to be in 2 sig figs. And you take 139 times 2.3, you get 319.7. Well, how do you make that into 2 sig figs? You round to 320. Our unit is centimeters times centimeters. So you're going to get centimeters squared. Now, in class, you're going to have time to work on a sig fig worksheet. and metric conversions. The metric conversions worksheet we really didn't talk about too much. That should be mostly a review, and we did the sig fig math there. So that's what you'll have in class tomorrow. And like I said, the benefit of the flipped classroom is anytime you have a question, look at the notes, and then we get a chance to do problems in class. So you do that, and that's how easy it is. So we'll see you in class tomorrow, guys.